Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show CFD analysis through an Orifice meter. Here in this case, what will be happening is massless particles of water will be flowing through this Orifice meter, and at different cross sections we can check the velocity profile, temperature profile, and also pressure gradient, etc. Right? Let's get started. First of all, we have to model this Orifice meter, right? Let's model that one using SolidWorks. We'll take the right plane for modeling. Right plane normal to sketch, then two concentric circles will be there. Let's provide smart dimension to that one as the inner one 75 millimeter and the outer one 80 millimeter. So drawing is ready, green check and exit from the sketch. Select the sketch again and features extrude boss base. And while extrusion, we have to select the middle plane. And let's provide extrusion depth equal to 200 millimeter. Okay, done, green check. Next one, we have to provide the location of the Orifice meter, right? So we have to select that right plane again, normal to sketch again, two concentric circles will be required. Done. Let's provide smart dimension to the inner one as this one equal to 30 millimeter. Okay, done. So green check and exit from the sketch. Now select the sketch again and this one to be extruded with a lesser thickness. Let's that one provided from the middle plane again. Let's extrude this one by 5 millimeter. So the Orifice meter is ready, right? Now we can do one thing while viewing these flow patterns through this pipe. This one should be transparent, so we'll make it transparent. Select this object and change transparency. It's transparent from outside, again from transparent should be changed from inside also. Select these objects again. Change transparency. Done. Again this inside orifice also that should be changed. Select that part, control select other part also, change transparency. It is a transparent orifice meter right now. Okay, done. Next one, for CFD analysis, it is very important to see that closed volume should be generated inside, right? So we have to provide some leads at the entry and exit point. We can provide the leads from closed solution tools. Create leads. Now for getting leads, you have to select the surface only. Let's select the entry point as the first surface. So first lead is created at phase 1. Now to select the second phase. So second lead is also created. Two leads we have provided, right? Okay. And save this by the name of Orifice. Okay. Let's save it. The model is ready and going for analysis. Now before going analysis, is to check the geometry is okay or not. So let's check the geometry. Internal analysis is going on, so we'll click internal and check the geometry. So it is successful, so geometry is okay. Next we can do one thing. We have to see that what fluid volume is generated inside or not. Okay, so done. So our model is completely ready for flow simulation. Now for starting flow simulation, we have to create that environment created with wizard, and let's provide the name of this project as project 1 itself. Next, select the unit as SI unit. Next, and it is an internal analysis. Next, select the liquid as water. Next, and if you don't know these default thermal conditions and roughness, let's skip this part, and next, and finally finish this one. Right, now you can see this computational domain is created. Right, we can do one thing. We can change this domain by we can increase this domain also by dragging a little bit. We're going to see that like all objects should be inside this one, right? Our Orifice meter should be inside this computational domain. Can drag a little bit. Is inside this one, right? Fine. Okay. Now we can do one thing. For providing these boundary conditions, we can make this computational domain as hidden. Okay, we can apply boundary conditions. Now while applying boundary conditions, it is better to see that object in the segmented portion. That means we can cut it from the front plane. Okay, we have cut this one from the front plane. Now we can apply boundary conditions, right? So insert boundary conditions, and inlet mass flow rate, let's provide this one equal to 0.205 kg per second. Select that face, grain check. So inlet boundary condition is applied. Now at the exit level you have to apply pressure equal to atmospheric pressure. Again apply boundary conditions. It will be pressure at the exit level equal to environmental pressure, right? We select that surface of exit level, grain check. So both the boundary conditions have been applied, right? We can make the object as complete object. Now we can select some goals. We're having a lot of goals like global goals, point goals, surface goals, volume goals, etc. In this case we'll apply global goals, and we want to see average velocity, grain check, and also by the same time we can see some other goals like surface goals, average velocity across the surface. We want to see the surface. Let's select that empty surface, select other, lead 1. Okay, next one we should run this. While running this one, it is very important to see this solver windows. Actually from the solver window we can visualize what is actually happening inside. Like here in this case we can see velocity flow rate. At the beginning it is almost 0, but at the location where the orifice is there, in that case velocity is very high. It is in the red region, right? Solver has finished, so we can go for the results. Results are ready at this moment. We can see from the beginning first. From the cut plot we can see the results first. Cut plots, insert cut plots. That means along a specific plane you can see velocity, pressure, temperature, etc. Right? We're going to see pressure or velocity. Let's see the velocity at the beginning across the front plane. Okay, you can see velocity in the form of contours also, or isolines or vectors, right? Vectors will point in directions, right? Okay, isolines also. Let's see that. These are the isolines, these are the vectors. Edit cut plot. First clear and hide, then edit cut plot. So what we plan to do is, we'll see only contours and going to see the velocity, not vorticity, velocity you want to see, right? Okay, again it is seen that at the orifice level only the velocity is very, very high. Before that it was normal, it was in the range of 0.002 meter per second, but after the orifice the velocity is 0.011 meter per second. You can see the pressure distribution also. Let's see pressure distribution. You can see the pressure at the entry point is very high, and while exit it is minimum one. You can see the temperature distribution also. Temperature actually we are not having any kind of change, it is almost similar, right? Now we can do one thing, like cut plot we can see in the form of animation also. First clear and hide, and cut plot, animate. Let play. This is showing temperature. We'll see velocity again. You can see the cut plot of velocity flow. The pattern it is showing that it is parabolic. That means at the entry level you can see the flow pattern is parabolic, so it is laminar at the entry level. Okay, you can see different things like pressure. The pattern is same also for velocity and pressure. Let's clear and hide this part. Cut plot 1, clear and hide. Next we'll see surface plots. It will show velocity pattern along different surfaces. We use all faces and want to see velocity, right? Okay, you can see here it is like throughout the surface the velocity is 0. That means it is following what is expected, right? That means at the boundary level, because of drag force the velocity is minimum, it is 0. And if you see the middle point, you can see here at the middle point velocity is higher, it is in the range of 0.207 meter per second, right? Next one we can do one thing. Now first we have to clear and hide this part. Surface plot, clear and hide. Next part is very important. When you see flow trajectories, that means the flow of water from left end, from starting end to the finishing end throughout this orifice meter, we'll see, right? Flow trajectories, insert. Now what to see velocity in the form of arrows only, right? We'll see both in the form of arrows and pipes also. First let's see in the form of pipes, right? Select other, lead one orifice. This should be phase 1, yes. Green check. Now you can see here the pattern. Yeah, you can see here is pattern is like actually after this orifice meter velocity is very, very high, so it is following the straight line. It is not moving, it is not following the actual path what it was at the beginning, right? We can see in the form of animation or play it. So what we'll do is flow trajectories, clear and hide, and let's play that part again. can see this flow pattern through this orifice. That means after passing through this orifice, velocity is high, and that is in the range of 0.207 meter per second. Right, now we can change the pattern a little bit. We can see this one in the form of arrows only, right? So clear and hide, flow trajectories, clear and hide, flow trajectories, edit definition. We are to see in the form of arrows only, right? Green check, clear and hide, and flow trajectories, clear and hide, flow trajectories, play. We can visualize how these massless water particles are moving throughout this orifice meter. And it is also understood that it is following continuity equation, as at the entry level cross-sectional area is very high, so velocity will be less, and at the orifice meter, as it is cross-sectional area is less, so velocity will be high. So Q equals to A1 B1 equal to A2 V2. Continuity equation is followed here perfectly, right? Clear and hide. We can see velocity patterns. By the same time, you can see other things like pressure also we can check. Let's see pressure. Again, it is seen at the entry level pressure is very high, and while passing out, it is in the normal level equal to atmospheric pressure, as following in the boundary conditions, right? Okay, let's clear and hide this part. Now finally, you have to see the particle studies. In particle studies, we'll see how these massless water particles will be moving from entry to exit. It will be injected from the entry level. Massless fine particles of water will be injected from the entry level, and it will be moving from entry to exit throughout this. We'll see the total pattern of massless particles, how these will flow. Okay, starting these particle studies, it will be started with the wizard. Next we have to select the liquid. We want to select water, and let's select the surface from which we are to inject these massless water particles, right? Select other, then lead one, green check. Next, we have to run this particle study and see the injection flow. Play. It's showing pressure. Actually, pressure distribution is there. At the beginning, pressure is very high, and while passing through this orifice, pressure is less, equal to atmospheric pressure, right? We'll change the velocity. Let's change it to velocity, average velocity pattern. Again, we are following the same trend what we saw before. Massless water particles are moving from entry to exit through this orifice. At the orifice, we are having some kind of deviation, and as at the orifice level, water cross-sectional area is less, so velocity is increasing. And velocity after this orifice is in the range of 0.206 to 0.207 meter per second, while at the entry level it was 0.201 meter per second to that high level. Okay, and finally we can do one thing. We can generate a report. One report will be generated. In that report, all this data in the form of these graphs and these videos all will be inserted. Okay, this is all about our today's analysis or studies. This is a very basic one. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.